Putting steel on target. It's a phrase that gunners and aviators use when they've scored a direct hit. But hitting that target, whether it was a tank crossing an open desert or an aircraft flying at 30,000 feet, wasn't always the easiest thing to do. Misjudging the wind speed, temperature, or even the humidity could send a rocket or a bomb off course. The most dramatic advance of military technology in the last 5 decades has been the development of precision guidance for virtually every class of weapon. Making weapons smart means putting that steel on target.
4, 3, 2, 1, impact. Boom! There's a hit. There's a shack. And oh yeah. Secondaries, big time secondaries. Coming left. Go to 275.
Desert Storm began with a bullseye. The guided weapons of the coalition forces found and destroyed their Iraqi targets with near impunity. The enemy's war machine vanished in the blink of an eye. New weapons like smart bombs carried by the F-117 stealth fighter displayed the unprecedented power and precision of the high-tech tools of war. Facing a powerful, well-equipped enemy, General Norman Schwarzkopf decided that before his ground troops could free Kuwait, he must first crush the Iraqi Air Force.
Our goal was to put them into shock and destroy their ability to defend their homeland. We were able to do that by having massive attacks across the full spectrum of targets, primarily command and control and his air forces, and also the surface-to-air missiles.
Targeting strategy from the start was to take down his ability to command and control his military, whether it be in the air or on the ground. Of course, we were obviously most concerned about taking it down in the air to start with.
Desert Storm would begin at H-hour, 3 a.m., January 17th, 1991. After they took off from their Saudi air bases, F-117s topped off their fuel tanks and turned towards the most heavily defended targets in Iraq. 1 hour and 26 minutes before H-hour, the Navy launched the first of almost 50 Tomahawk land attack missiles. They would reach their targets a few minutes after 3 a.m. At H-hour minus 21 minutes, 8 Apache helicopters crossed the Iraqi border and destroyed 2 early warning radar installations with their Hellfire missiles. At H-hour minus 9 minutes, the first bomb to fall from an F-117 hit an Iraqi command center in the southern part of the country. Minutes later, 32 F-117s headed into downtown Baghdad. Their next target was Baghdad's central telephone facility, dubbed the AT&T building. At H-hour plus 4 seconds, Saddam Hussein's communications network was rubble. Command bunkers called sector operating centers and interceptor operating centers were bombed.
So right at H-hour, immediately by H-hour, his ability to see airplanes coming in from the south was degraded. The IOCs and the SOCs were taken down. His ability to communicate was taken down, and the city went black.
It was almost eerie to how precise the plan unfolded in the first 24 hours. For all practical purposes, there were absolutely no glitches.
We totally overwhelmed him from the get-go. So he never was able to recover from that first 24 hours in terms of being able to effectively use the defense against our capability.
To ensure that the weapons hit their intended targets, special guidance packages and fin assemblies were fitted into the nose and tail of otherwise ordinary high-explosive bombs. The seeker heads house a detector that can lock onto the reflection of a laser beam aimed at the target. The seeker controls the fins and the bomb's trajectory as it falls toward the source of the reflection. These dumb bombs were made smart. The laser beam that's aimed at the target can come from a pod carried by the attacking aircraft or from handheld laser rifles aimed by ground troops. The stealth fighter carries the GBU-27, a 2,000-pound laser-guided bomb made stealthy with a coating of radar-absorbing material.
On day 4 or 5, I put 11 F-117s and 4 F-111s, dropping precision bombs. And we put 7 bridges in the water the first night.
Iraqi engineers hastily built pontoon bridges. Those too were destroyed. To take out the enemy radar sites with certainty, the Air Force used HARMS, high-speed anti-radiation missiles. HARMS are designed to home in on the signals produced by unfriendly radar systems. The HARMS were flown into combat on F-4Gs, known to their crews as wild weasels. The crews knew that to get a good fix on the locations of the Iraqi radars, they had to put themselves in a very vulnerable position. Weaseling was a dangerous mission. Unlike most fighter pilots who quickly break away to avoid the radar of enemy surface-to-air missile sites, the weasels turn their jets into the source of the enemy radar emissions. If the Iraqi crews manning the missile sites responded quickly enough, they might be able to launch a SAM and shoot down the approaching wild weasels. But the weasels and their HARMS beat them to the draw every time.
Because of that fear of the ability to put harms on them and kill them, they were very reluctant to have their radars up for any length of time. So consequently, they were not able to get good SAM shots at us.
No impact yet. Okay, but there's 2. Boom, boom. Secondaries, big time. 3, 2, 1. The hit. That's a hit.
7,400 tons of precision-guided munitions were dropped on Iraqi targets during Operation Desert Storm. Hardened aircraft bunkers, some with concrete walls 10 feet thick, couldn't survive the impact of even one of the Coalition Air Force's smart bombs.
I think that the one thing that this war has done from an air power standpoint, without a doubt, that it has changed mass to precision. Where we dropped 30,000 bombs to take out a target in World War II and 300 bombs in Vietnam, we dropped 1 in Iraq.
The airmen of the First World War were just beginning to explore the potential of their new technology. Machine guns turned the former reconnaissance airplanes into formidable attack weapons. Small explosives taken aboard the airplanes and dropped from their high vantage point could wreak havoc on the battlefield. Shortages of aerial bombs forced some airmen to improvise.
So we'd take 3-inch shell casings and just chunk them full of all kinds of stuff, everything we could put in there, and make our own bombs. And we would get over a road while we were supposed to be observing for enemy activity and everything. We'd see a line of trucks. So we'd try to work out our windage, and we'd let them go, see. And then we'd fire them back, and we'd try to watch the trajectory as they dropped. And sometimes we'd be 200 or 300 yards off target. And we had no smart bombs, they were just blah. And we made some good hits. We got pretty good.
Midway through the war, the use of aircraft for bombing missions grew enormously. New, larger bombs with intricate fusing devices protected ground crews and pilots from accidental explosions. But the additional weight of the iron bombs degraded the performance of the smaller fighter planes. Larger biplanes with more powerful engines were built to carry heavier bomb loads into combat. German twin-engine bombers could sling 700 pounds of bombs beneath their wings. But putting the bombs on their intended target was still more a factor of luck than design. After the war, the size of aerial bombs continued to grow. Under the guidance of General Billy Mitchell, the accuracy of level bombing improved. The Germans put their faith in dive bombers.
At that time, there were no level bombers in the world that were really effective. Level bombers didn't hit their targets. Level bombers often didn't find their targets. Whereas the Stukas were like a well-keyed-in artillery piece. They blasted in and would hit exactly. The Stukas would appear over a point precisely when the tanks wanted them to be, would attack, and Stukas were able to dive very close to the ground and consequently were very accurate.
Dropping bombs from such a low altitude put the pilots within range of anti-aircraft artillery. But dive bombing, regardless of the dangers, remained the best chance for hitting enemy targets with pinpoint accuracy. All that changed in 1935 when the Boeing Aircraft Company delivered the first B-17 heavy bomber. These four-engine, heavily armed aircraft, each with a crew of 10 men, were built to deliver their 5,000-pound payload across a continent. The heart of the flying fortress was the top-secret Norden bomb site. During a bomb run, the B-17 had to fly straight and level, with no choice but to endure the attacks of enemy fighters.
You had to have at least 30 seconds of absolute straight and level flight. Minimum 30 seconds. Would be great to have 70 seconds because you could synchronize better. When the bombardier had identified the target area, he had the capacity to swing the sight onto the target, and then he could clutch into the autopilot. When he clutched into the autopilot, the bomb sight controlled the airplane. It was always a great relief to release the bombs for some reason. I guess you figured the job was really done. You go in for the United States and come back on your own.
But even with the Norden bomb site, hundreds of bombs and hundreds of planes were still needed to guarantee that a mission would be successful. Very often, the bombs fell wide of their intended targets and hit civilian areas, or landed harmlessly in open fields. Near the end of the war, the Air Corps developed a rocket-powered bomb called the Disney Swish. A rocket booster was added to an ordinary high-explosive bomb. Fins were attached to stabilize the weapon. Once the 18-foot-long Disney Swish was dropped and cleared the bomber, the rockets would ignite and propel the bomb to its target. The new bomb was used to penetrate the thick dirt and concrete that protected deep bunkers and submarine pens. In the Pacific, Japanese suicide pilots attacked Allied shipping with planes propelled by rocket boosters. A large explosive was packed into the nose of the aircraft. Even though these were guided bombs, they weren't called smart. The Allies nicknamed the suicide rockets Baka bombs, the Japanese word for foolish. The Allies tried the same idea. Instead of suicide pilots, the Air Force used remote control equipment and radio transmitters to guide aircraft filled with TNT. For the Allies, the first effective precision-guided bomb was known as Raison. A tail assembly mounted to a 1,000-pound general-purpose bomb carried a radio receiver and a gyro stabilizer. A powerful flare helped track the bomb's fall. The operator's control stick could adjust the rudders and elevators as the bomb fell to its target. The bomber aircraft carried a radio antenna to transmit the bombardier's control signals to the Raison bomb. Raison required the aircraft to stay on the bomb run longer than normal so that the controller could observe the path of the bomb. Raison was not used in combat, but Azon, an earlier, less sophisticated version, was dropped on some bridges and dams. This first smart bomb proved to be 30 times more accurate than a conventional bomb.
In the immediate post-war years, atomic weapons received the greatest attention from military research and development. But there were other advances that would increase the range, power, and effectiveness of more conventional weapons. Armored vehicles, warships, and all types of aircraft took on board new classes of weapons that provided unprecedented levels of detection and tracking of targets.
Radar guided the United States Navy's BAT, an air-to-surface missile. 12 feet long, the BAT carried a 1,000-pound warhead. In April 1945, the BAT was targeted against a Japanese warship 20 miles from its release point. The BAT scored a direct hit. On an Air Force test range, a similar winged bomb homed in on its target with the help of a small television camera mounted in its nose. The crude system proved quite effective.
As the technology continued to progress, we found that we could indeed build a guidance system accurate enough to deliver a weapon from a fixed-wing aircraft at a ground target, an individual single tank, and have a high enough probability of hitting that tank that it was worthwhile building such a guided missile. The Maverick uses a TV or maybe an infrared-like sensor to acquire the target up in the nose of the missile. The pilot points the missile seeker at the target. When the missile seeker is locked on, is then able to fire those missiles, turn and go home, and not have to stay with that missile to the target, not have to overfly the target to drop bombs, and yet have a high assurance the target will be destroyed. Such missiles as a Maverick have had success rates in the order of 80 to 85%, which means that 85% of the time, the pilot knew that when he launched that missile, it would indeed hit and kill the target. It gets his job done. He kills the target he wants to kill, doesn't make holes all over the ground in places he didn't want to destroy. A single missile killing a single target and accomplishing the purpose of the mission.
In 1983, 10 years after the Maverick missile entered service, Rockwell International developed a modular television guidance package, the GBU-15. A seeker head with a video camera and a controllable tail unit were built to fit over an existing 2,000-pound iron bomb. The image that the bomb sees is transmitted back to a television screen in the cockpit. A weapons operator in the aircraft uses a joystick to transmit signals back to the bomb to keep it on the proper course. The explosive power of its 2,000-pound bomb makes the weapon particularly effective against large, solid targets like bridges and warships. The GBU-15 can also be guided by a more advanced low-light infrared detector. Like the television seeker, the infrared unit also transmits an image back to the cockpit, but is used when a target is attacked at night. During the Gulf War, large F-111 Aardvark fighter bombers and F-15Es delivered the heavy guided bombs. The fighter bombers primarily struck targets that were likely to be heavily defended or that offered good contrast to permit effective lock-on by the television or infrared seekers. To overcome the low visibility caused by bad weather, the bombs were dropped above the clouds but only locked onto their targets after they had glided beneath the cloud cover. More bombs were dropped during the Vietnam War than were dropped to defeat the Germans and the Japanese in World War II. Countless raids by B-52s over the Vietnamese jungles often had the same effect as many B-17 missions over Europe, an expensive way to plow an empty field. In the 1960s, while television guidance was improving, another technology demonstrated its value for precision guidance of bombs. Lasers, a concentrated beam of light invisible to the naked eye, could be mounted in an optical system, aimed and focused even on moving targets. In an Air Force project codenamed Pave Knife, lasers were mated with television cameras in pods. When a target is selected, its image appears on the television screen monitored by the pilot or weapons officer on the plane carrying the laser designator. The designator then sends out a beam of laser light that the officer aims by moving a small joystick. The two main elements in a laser-guided bomb are the designator, which directs the beam at a target, and a laser-seeking device attached to the bomb. An onboard computer converts signals from the laser seeker into commands that move the fins to keep the bomb on target. The laser beam must remain centered on a target while the bomber maneuvers into position and while the bomb is falling. Since the seeker responds only to the precise wavelength of the beam sent by the designator, it cannot be confused by other light sources. The bomb was named the Paveway and entered service in the late 1960s. 25,000 laser-guided bombs were used in Vietnam. The new bombs could be released from safer distances, and their accuracy proved far greater than any other previous bombing technique. A weapon that could be dropped with high expectations that it would hit its target precisely. The same basic technology went to war 20 years later in the F-117. First in 1989 against one of General Noriega's Panamanian airfields. Then again in 1991 as the United States joined a coalition of nations fighting Iraqi leader Saddam Hussein. Experiments to attack distant targets with a self-propelled bomb began in 1917. With the help of Orville Wright, the Army attached wings and a 4-cylinder engine to a bomb and rolled it down a launch ramp. The Kettering bug did fly, and a gyro stabilizer kept it on course. But the gasoline engine so limited its range that the bug never saw action. It wasn't until Hitler's Third Reich began building jet and rocket weapons in the late 1930s that a self-propelled bomb would show its value in combat. The FZG-76, better known as the V-1 for Revenge Weapon 1, carried an 1,800-pound warhead. The winged missile was powered by a pulse jet of captivating simplicity. Tests of the airframe and motor revealed that the weapon was simple to maintain and almost foolproof to run. As the motor moved through the air at high speed, the power was produced in a series of pulses. Shutters at the front end admitted air into the combustion chamber and drew in a spray of fuel. The mixture was ignited and burned rapidly. The back pressure forced the shutters to close, and the jet exhaust propelled the machine forward. The intermittent combustion of the fuel gave the V-1 a telltale sound. A ramp and booster rocket were used to start the V-1 on its course. At 3:30 a.m. on June 13, 1944, the first V-1 was fired across the English Channel toward London. 9 more were fired in rapid succession, but only 4 bombs made it to England. Londoners came to recognize the raucous noise of the V-1 and named it the Buzz Bomb. The guidance system was simply an autopilot. When the pulse motor cut out, the V-1 would tumble to its target. Because of its large size and top speed of only 390 miles per hour, anti-aircraft artillery gunners could track the buzz bomb and shoot it down. Less than 1/5 of the V-1s fired at the British Isles actually exploded anywhere near the target area. Of the 13,000 flying bombs launched against England, only 2,419 ever hit London. Barrage balloons tethered with steel cables tore the wings off 232 of the unsuspecting weapons. Pilots of the RAF chased the robot bombs and shot them down. In the winter of 1944, the Belgian city of Antwerp became a target of the buzz bombs. The Germans hoped to weaken the port city on the eve of their last offensive against the Allies, the Battle of the Bulge. In an elaborate operation known as Antwerp X, a Central Allied command post dispatched American anti-aircraft gunners to the perimeters of the city. When observers spotted incoming buzz bombs, the command center could alert other air defense positions and pass on the direction and range of the approaching weapons. Of the 5,000 V-1s fired at Antwerp, only 211 ever detonated on target. The coordinated fire from the ring of AAA batteries brought down most of the V-1s. While gunners fought the flying bombs from the ground, heavy bombers tried to knock out the V-1 launch sites from the air. But the launching ramps were well camouflaged and built to withstand repeated bomber attacks. The Allied Air Force built a replica of a V-1 launch site at Eglin Air Force Base in Florida. There, perhaps a weakness could be found, or a bombing technique developed that could destroy a launch site. Level bombing didn't work. But low-level bombers could find and hit the difficult targets. In their advance toward Berlin, Allied soldiers captured many of the V-1s. Most of the buzz bombs were destroyed, but many that were found intact were sent back to the United States. The American Air Force redesignated the weapon the JV-2 and began its own cruise missile program. In Air Force laboratories, every aspect of the buzz bomb was closely examined. Its aerodynamics, guidance system, propulsion, and launching systems were all studied. Captured German V-2s, the giant liquid-fueled rocket fired against the cities of London and Antwerp, were brought back to the United States and tested. In 1947, the Navy began Operation Sandy. V-2s launched from aircraft carriers were the first step in finding a way for warships to strike distant land targets. From submarines, the Navy launched the Loon, their version of the German V-1. Everything found in German weapons labs were figured out and tested. Navy weapons designers incorporated what they discovered in their own more advanced rockets. The Regulus was the Navy's first intercontinental nuclear missile. It adapted features first seen on the V-1, including booster rockets that helped the jet-powered missile clear the launch deck. The Regulus could be launched from submarines, although only while surfaced. Radar control kept it on course. In In 1955, the Air Force launched its first operational cruise missile, the Martin TM-61 Matador. Using a simple radio navigation guidance system, the Matador picked up radio signals transmitted from 2 ground stations. It then used these signals to calculate its own position. The Mace, fired from a hardened bunker, compared data on a film strip with the terrain beneath the missile in flight and corrected any deviation in its course. The U.S. Air Force deployed the world's first intercontinental range cruise missile in 1959. Northrop's giant jet-powered SM-69 Snark carried a thermonuclear warhead up to 6,300 miles. The Snark was able to make its attack at low altitude and carried an unjammable star tracking guidance system. In 1976, tests began on the air-launched cruise missile. Once released, an internal navigation system would take over and guide the missile. About the same time, the Navy introduced its Tomahawk land attack missile. A TLAM can carry one of 4 distinctly different warheads. An anti-ship warhead for use against ocean-going targets, a 1,000-pound explosive warhead to send against targets inland, a 3rd warhead dispenses submunitions, small bomblets against airfields and other softer structures.
The 4th type is the nuclear land attack missile. All of the nuclear land attack Tomahawks have now been taken out of service.
The brain that makes the Tomahawk smart is the guidance system.
The land attack Tomahawks have a system called TERCOM, Terrain Contour Matching. As it enters the land, it starts picking up contours of the ground which were previously surveyed by satellite, digitized, and put into a computer. As the missile flies over the land, its radar looks down, compares the terrain with what's on its digitized tape. When they match, it knows it's going the right direction. If it doesn't match, it then looks for the exact path it should be taking. And it follows this to its target. It then uses another guidance system which cuts in and guides it to within literally a few feet of the aim point. One of the interesting aspects of the Tomahawk is it's the size of a standard torpedo. This means you can put it in a submarine and launch it out of a submarine torpedo tube or launch it out of a vertical launch tube in the submarine. All U.S. cruisers and destroyers being built today have vertical launch tubes that could take a Tomahawk or another missile. In addition, we have box launchers for Tomahawks we've put on battleships and on cruisers. Thus, you have an exceedingly versatile weapon capability there, in that virtually any cruiser, destroyer, or battleship in the U.S. Navy today can fire a Tomahawk. In the Gulf War of 1991, we launched almost 300 land attack Tomahawk missiles. They proved very effective. It was more accurate than we predicted it would be.
Bomb damage assessment of the Tomahawk showed that 85% of the aim points were hit.
Tomahawks were very effective because we can use them against highly defended targets and against anti-aircraft missile and gun sites without risking pilots. As a matter of fact, during the Gulf War of 1991, the only Allied weapon that operated over Baghdad, which was very heavily defended, were the F-117 stealth bombers and Tomahawk missiles. frightened the Iraqis because they knew they were unmanned and they could see them. The Tomahawks came across the countryside at 20, 30 feet at only a few hundred miles an hour, and they could actually see them coming down the roads.
Pinpoint accuracy replaced brute force.
I can see missiles of the future, not only selecting and being able to distinguish, say, a target from a building or a rock, but being able to tell that that target is a tank, a truck, a helicopter, and who built it and what force it belongs to. Say, yes, that's indeed an enemy tank, not a friendly tank. That's the next level of sophistication that we really want to go to with our, instead of smart weapons, let's call them brilliant weapons. Bigger computers, more accurate sensors, making the decision in flight as to who's good and who's bad, and doing a good job of it.
Smart weapons have certainly revolutionized warfare. They are more accurate than human-aimed weapons, especially if the human is in an aircraft that's flying, that's being shot at by enemy guns or missiles or being attacked by enemy fighters. The smart weapon is immune to all of this. It's generally immune to weather. So you have an accurate weapon, flexible weapon, and one that does not risk an American pilot.
It is easier to explain in many ways the workings of machines in battle than it is the workings of men. But gadgets have not replaced guts. The quality of weapons has been a much less significant factor in victory than has the quality of manpower.
Modern warfare is no longer fought with weapons born in the industrial age. They are fought with weapons of the computer age. This is an era where smart weapons acquire and destroy their targets with pinpoint accuracy. Conquest on today's battlefield means a victory of precision over mass.